Hello and welcome back to the Deep Dive. It is absolutely fantastic to have you here with us today.
Great to be here.
Usually when we talk about artificial intelligence,
Yeah.
we're looking at the fireworks, we're looking at the magic tricks,
Yeah, the flashy stuff.
the flashy stuff, the chatbots that can write a sonnet in the style of a 17th century pirate, or, the image generators that can win art competitions against human painters. We've all been living in that wow phase for the last year or two, haven't we?
It has been a party. A very loud, very expensive, and a very exciting party.
Right.
Everyone has been in this phase of pure discovery, just poking the bear to see what it does.
Exactly. But I feel like the lights are coming up, the music is turning down, and the bill is coming due. We are moving from the party phase to the cleanup phase.
Yeah.
Or maybe more accurately, we're moving from the art of AI to the engineering of AI.
That is the perfect way to frame it. The wow factor is great for a demo or for getting venture capital funding.
Sure.
But if you are actually trying to build a business on top of this technology, if you're trying to build a system that handles 1 million customers without going broke, without crashing, and, without hallucinating wildly, you realize pretty quickly that picking a smart model is just the absolute tip of the iceberg.
It's the difference between buying a Ferrari and actually running a Formula One racing team.
Yes.
One requires a checkbook, the other requires a massive amount of logistics, strategy, and engineering.
Precisely. And that is why I am so excited about the source material we are digging into today. It is a technical guide titled The Foundation Model Orchestration and Lifecycle Guide.
Orchestration and Lifecycle. It sounds a bit dry, doesn't it?
It does.
It sounds like something you'd read in a basement.
It sounds dry until your application crashes on Black Friday. Then it sounds like the most exciting document in the world.
Good point.
This guide is effectively a reality check. It steps away from the magic and gets right into the plumbing. It asks the hard questions. How do we select these models? How do we configure them? How do we stop them from costing us a fortune? And crucially, how do we rescue them when they inevitably fail?
And the premise here is really interesting right off the bat. The guide suggests that choosing an AI model today isn't like buying a software tool. It's not like buying Microsoft Word or a subscription to Slack.
No, not at all.
It suggests it's more like hiring a team.
I love that perspective. It is a profound shift in mindset.
Right.
When you buy a tool, you look at specifications, you look at a feature list. But when you hire a team, you look at dynamics, you look at fit. You don't just hire the smartest person in the world for every single role in your company.
Right. You wouldn't hire a Nobel Prize-winning theoretical physicist to man your reception desk.
Exactly. Think about that for a second. They would be incredibly expensive.
Insane.
They would take 3 weeks to ponder the philosophical implications of how to answer the phone. They would probably get bored within an hour and start redesigning your phone system instead of using it. And they might not even be good at it. And honestly, they might be terrible at the actual job of being friendly to customers.
So in this analogy, the physicist is the massive trillion-parameter model that everyone wants to use, the state-of-the-art one that just came out last week.
Correct. And the receptionist is the task. If the task is simple, you don't need the physicist. You need someone reliable, fast, and cost-effective.
So the mission of this deep dive is to move beyond the hype. We want to get into the engineering reality. We're going to talk about things like circuit breakers, PEFT, model routers, and graceful degradation.
It sounds like Jargon City.
It does, but I promise we are going to unpack all of it. We're going to decode this so that by the end of this hour, you won't just know what these words mean. You'll understand why they are the difference between a toy and an enterprise system.
And what's fascinating is that while the terms sound technical, and they are, the concepts are actually deeply strategic.
How so?
They connect directly to business value, to reliability, and to keeping your CFO from having a heart attack when they see the cloud bill.
Okay, let's dive in. Section 1, the selection matrix. Because, let's be honest, the first problem anyone faces right now is the paradox of choice.
Oh, absolutely. It's overwhelming.
It feels like a new world-changing model comes out every Tuesday. You have the proprietary giants, you have the open source rebels, you have large models, small models, medium models. If I'm a CTO or a lead engineer, how do I stop the spinning in my head?
Well, the guide suggests we need to stop looking for the best model.
There is no best.
There is no such thing as the best model. There is only the right model for your specific constraints. And to find it, they propose a matrix of metrics, a framework.
A checklist, basically.
A checklist, yeah. A way to think systematically.
And the first metric they highlight is capabilities and modalities.
This goes back to your hiring analogy. What do you actually need the model to do?
Right.
Modality refers to the form of the data. Does it need to process text? Does it need to analyze images? Does it need to write code? Does it need to hear audio?
That seems straightforward. If I need to analyze X-rays, I need a model with vision capabilities. Simple enough.
Right. But the nuance is in the capability part, specifically the reasoning capability. This is where the magpie effect kicks in.
The magpie effect. What's
It's
that?
my term for it. Developers see a shiny new object, a model that scores 99% on a physics benchmark, and they say, we have to use that one.
Oh.
Even if their use case is just summarizing customer support emails.
So they are bringing the physicist to the reception desk.
Exactly. Let's break it down. If you are building a chat with your data and a RAG or retrieval augmented generation.
We've all seen those. You upload a PDF and ask a question.
Right. And most of the hard work in that system is actually finding the right document or the right chunk of the document. That's the retrieval part. The AI, the generative model, its job is just to read a paragraph and summarize it. That is a low reasoning task. You do not need a model that can simulate nuclear fusion to summarize a paragraph.
But if I'm building an automated coding assistant.
Completely different story.
Why?
If you need a model to debug complex Python scripts, to understand system architecture and spot security vulnerabilities, you do not use a lightweight model. It will hallucinate syntax. It will introduce bugs.
So it'll look like it's working, but it's actually making things worse.
Much worse. You need the physicists for that one. You need high reasoning capabilities. You need a model that was trained on billions of lines of code.
So bigger isn't always best? It's about matching the brain to the problem.
No.
Overkill is a real risk.
Correct. Often a smaller, more specialized model, or even a general model that isn't state-of-the-art, might be faster, cheaper, and frankly, perfectly adequate for the specific task at hand. This is about avoiding overkill.
Okay, so once we figure out if we need a truck or a scooter or a physicist or a bookkeeper, we run into the constraints. The source lists, token limits, and latency is the big ones. Let's start with token limits. I hear this term context window all the time. It feels like the new megapixels war in cameras.
It really is. Everyone is bragging about their size. I have 100K tokens. I have 1,000,000 tokens.
A billion.
Right. It's a marketing race.
What does it actually mean in practice for a developer building something?
Okay. Think of token limits as the memory span of the conversation, or visualize a desk. The model is a worker sitting at a desk. The token limit is the size of the desk.
Okay, I like that. A physical space.
Every document you give the worker, every instruction you give them, every question you ask, and the paper they're writing their answer on, it all has to fit on the desk at the same time.
I see. So if it's not on the desk, it doesn't exist to the model.
It is completely forgotten and it doesn't exist.
So if I have a 500-page legal contract and I want the AI to find the loophole in clause 42, but the desk is tiny.
If the contract exceeds the token limit, the model physically cannot see the whole thing.
It falls off the desk.
It falls off the desk. It's like asking someone to summarize a book, but you rip out the last 200 pages. They can't do the job. The context is lost.
That is a huge constraint for business applications. I'm thinking legal, medical, finance.
It is critical. If you're building a system to analyze large legal documents, medical records, or financial history, you prioritize a model with a massive context window, a huge desk over almost everything else.
Really? Over reasoning ability.
Well, within reason. But you might accept a slightly dumber model if it has the capacity to actually read all your data. A genius who can't see the evidence is useless.
Got it. Now let's talk about latency. That's just speed, right? How fast I get my answer.
It is speed, but in the context of user experience. We measure this in a few ways, but the most important one for humans is TTFT.
PTFT, another acronym.
Time to first token.
Ah.
How long does it take from the moment you hit enter until the very first word appears on the screen?
The I heard you metric.
Exactly.
We've all been there, staring at the little spinning wheel, wondering if the internet died.
That is high latency. And here's the trade-off. Usually, the smarter the model, the higher the latency.
The bigger the brain, the slower the thought.
Kind of. It takes more computational power to think through a complex answer. The physicist takes longer to ponder than the bookkeeper does to add two numbers.
So if I'm building a customer service bot that chats in real time on a voice call,
you cannot have a 3-second pause after every sentence.
it'll be awful.
It would be excruciating. The user would hang up. In a real-time chat or voice interface, speed low latency trumps depth. You need that answer to start streaming immediately.
Even if the full answer takes a few more seconds to generate, just seeing that first word appear makes it feel responsive.
It does. It shows the system is alive and working.
But what if I'm not doing real time? What if the user isn't there waiting?
This is the key distinction the guide makes. Real-time user experience versus background batch processing.
Give me an example of batch processing.
Let's say you are a marketing firm. You have a million tweets about your brand from the last month. You want to analyze the sentiment of every single one to write a report for your boss.
Okay, a big analytics job.
You run this script overnight.
I'm asleep while it runs.
Exactly. You do not care if it takes 5 seconds per tweet or 10 seconds per tweet. Nobody is watching the spinning wheel. In that case, you completely ignore latency.
So what do you optimize for then?
You optimize for accuracy and cost. You use the smartest, most accurate model you can afford, and you let it run for hours.
That's a great distinction. Is a human waiting for this?
Yeah.
If yes, speed is king. If no, speed is irrelevant.
Precisely. And that leads us directly into the third metric, which is the hard reality of business: cost and licensing.
The bill.
That-
The fun part.
The bill. And it's not just the price tag. With cloud-based models, you're usually paying per token, per word, essentially, both for the input and the output.
It always sounds so cheap, though. Fractions of a cent per 1,000 tokens. It feels like monopoly money.
It feels like nothing until you scale. It's the classic cloud bill shock.
I've heard horror stories.
Let's do the math. Suppose you pick that massive genius model because you just wanted the best. It costs, say, 6 cents per transaction.
Still sounds cheap. 6 cents for a brilliant answer.
Sure. But now imagine you launch your app and it goes viral. You have 100,000 users doing that once a day. That is $6,000 a day.
A day.
That is over $2 million a year just in API fees.
Wow. For a startup, that is a death sentence.
It is. We have seen startups burn through their entire venture capital funding in 6 months because they picked a model that was too expensive for their scale.
And what's the alternative?
If they had picked a smaller, optimized model that was perfectly good for their task, one that cost maybe a fifth of a cent per transaction,
Okay.
their bill would be $70,000 a year instead of $2 million.
That is the difference between a profitable company and a bankruptcy filing.
It really is. Engineers love the best tech. CTOs have to look at the unit economics. You have to ask, does the value of this task justify the premium model?
And then there's licensing. This is where the legal team gets involved.
Oh, absolutely. This is a major gotcha, especially with open source models.
Why open source? That's supposed to be the free option.
There is a misconception that open source means do whatever you want.
Oh, doesn't it?
Definitely not. Some open source licenses are permissive, like Apache 2.0 or MIT. You can use them commercially, modify them, sell the output. You are safe.
But there's always a but.
But others are restricted to research only.
Yeah.
You can play with them in the lab, but you cannot put them in a product.
Oh, that's a big one.
And then there are the copyleft licenses.
That sounds like a political term.
It's a legal term. It means that if you use this open source component, you might be legally forced to make your own application can you open source. It's viral.
Yikes. So I build my proprietary secret sauce app using a model with a copyleft license.
You might be forced to publish your secret sauce on GitHub for everyone to see.
My competitors would love that.
It's a minefield.
Yeah.
The expert view here is that you must vet the license before you write a single line of code. Do not assume.
So, to recap the selection matrix, we are matching the capability to the job, checking if the desk, the token limit, is big enough for our papers, deciding if we need speed, which is latency, or depth,
Right.
and ensuring we can actually afford it and legally use it.
That is the checklist. And the source actually suggests a practical exercise here. It challenges engineers to look at specific tasks, say, summarize a meeting versus debug this Python script, and justify their candidate choice based on these constraints.
I love that. It forces you to think critically. You can't just default to use the biggest one.
Exactly. It forces discipline.
Yeah, okay. Let's move to section 2. This is where things get really architectural. We've picked our model, or have we? Because the source introduces this concept of a model writer.
This is one of the most important architectural patterns in modern AI systems. It addresses the hard coding problem.
So, the problem as I understand it is this. If I hard code model X into my app, I literally write import model X in my code, and then next week model Y comes out and it's half the price and twice as fast. I'm stuck.
You are stuck. That is called vendor lock-in, and in the fast-moving world of AI, it is deadly.
Deadly. That sounds dramatic.
Well, think about it. The models are improving so fast that the best model today will be obsolete in 3 months. If you have to rewrite your backend code, redeploy your servers, and do a full QA testing cycle every time you want to switch models, you are too slow. Your competitors will eat your lunch.
So the solution is dynamic model selection, the model router.
Think of it as a middleman, or a traffic cop, or sticking with our analogies, a general contractor.
Okay, explain that one. The contractor.
Your app is the homeowner. You say, I need a wall painted. You don't care which plumber or which electrician they use, you just talk to the contractor. The contractor finds the best subcontractor for the job based on price, availability, and quality.
So the router's the contractor and the
Yeah.
models are the subcontractors.
Yeah.
Okay, let's unpack the tech stack here because the source gets specific. It mentions AWS Lambda, API Gateway, and app config. I want to walk through the life of a request to visualize this.
Let's do it. Imagine your user, let's call her Sarah, is using your app. She types a question, summarize this quarterly report. She hits enter.
Okay, Sarah hits enter. Where does the request go?
It hits the front door. That is the API gateway.
What does that do?
It standardizes the request, it checks Sarah's credentials to make sure she's allowed to be there, and it passes the package inside. It's like security at the front of a building.
Okay, so the request is inside the building.
Now it goes to the logic layer. That is AWS Lambda. This is a piece of code that runs in the cloud. Think of Lambda as the chef in the kitchen.
Okay, so the chef has the order. Summarize this report.
But here's the trick. The chef does not have a supplier hard-coded. The chef doesn't say, I always use OpenAI. The chef pauses and looks up at a digital screen on the kitchen wall.
And what is that screen?
That screen is app config. It is a separate service that holds your configuration settings. In app config, you, the restaurant manager, have set a rule. The rule says, current summary model is called Anthropic Claude.
I see, so the configuration is outside the code.
Completely separate. The chef, which is Lambda, reads the screen, which is app config, sees Anthropic, and sends the request to Anthropic.
And Sarah gets her summary. Everyone is happy.
Everyone is happy. But now, let's say tomorrow a new model comes out, Llama 3 releases, and it's super fast and cheap. You want to switch.
Do I have to retrain the chef? Do I have to rewrite the Lambda code? Do I need to call the developer at 2 a.m.?
No, you don't touch the code. You don't redeploy the software. You just log into app config, the control panel, and change the setting from Anthropic to Llama 3.
That's it.
That's it. It's like changing the channel.
And the next time Sarah hits enter.
The chef looks at the screen, sees the new name, and routes the request to Llama 3. Instantly.
That is incredibly powerful. It basically means no code changes to switch brains.
That is the holy grail. It decouples your application logic from the model provider.
The source uses this logic to suggest that we should treat models like a utility, like the power grid.
Yes. Think about the outlet in your wall. When you plug in your toaster, you don't care if the electricity is coming from a wind farm, a solar panel, or a hydro dam.
I really don't.
You don't care who generated it. You just want the voltage.
And the model router is the grid.
The router handles the sourcing. As a user, or even as an application developer, you just want the result. This architecture allows you to swap out the power plant, the AI model, whenever you want, based on cost, performance, or availability.
That is a game changer. It means you aren't beholden to one company. If one provider raises their prices, you could just flip the switch in app config and route your traffic somewhere else.
It creates a competitive market for your business. It puts you in the driver's seat.
And you could get even more clever with it, right?
Absolutely. You can get fancy with it. You can say, route all the premium users to the expensive, high-quality model and route all the free users to the cheap model.
Dynamic routing based on user tier. That's smart.
It allows you to optimize your margins in real time. Or you could route based on the type of question. Is this a simple question? Use the fast model. Is this a complex legal question? Use the slow, powerful model.
The router itself becomes intelligent.
It does. It's the brain of your AI operations.
I love that. But of course, things don't always go smoothly. Even with the best router, sometimes the power plant goes down.
Yes, they do.
Which brings us to section 3, resiliency patterns.
Keeping the lights on. Or what happens when the robot stops talking?
The source is pretty blunt here. Models fail, regions go down, APIs time out. It's not a matter of if, but when.
That is the mindset of a reliability engineer. You assume failure is inevitable, and you design around it. You don't hope for the best, you plan for the worst.
So strategy number 1 is multi-region deployment and cross-region inference. This sounds like Don't put all your eggs in one basket.
It is the geographic basket concept. Cloud providers have data centers all over the world. These are called regions: U.S. East in Virginia, U.S. West in Oregon, Europe and Ireland, etc.
And sometimes bad things happen.
Sometimes a hurricane hits Virginia. Sometimes a backhoe cuts a fiber optic cable in Frankfurt. Sometimes a software update goes wrong and takes down a whole region.
It happens more than people think.
It does. If your application is only living in US East and US East goes down,
Your application is dead. Your customers are staring at a blank screen. They're angry. They're posting on social media. It's a disaster.
total disaster. So cross-region inference means what?
It means your system is smart enough to detect that US East is having trouble. Your reader, our traffic cop, sees the roadblock. It automatically reroutes the request to US West.
So the user might experience a tiny bit more latency because the data has to travel across the country.
Exactly. Maybe it takes an extra 50 milliseconds. A human won't even notice, but they get an answer.
They get an answer, the service stays up. That is high availability. It's a fundamental principle of good engineering.
Okay, strategy number 2, circuit breakers. I know this term from my house. If I plug in the microwave, the toaster, and the hairdryer all at once, the circuit breaks to prevent a fire.
The engineering pattern is very, very similar.
How does it apply to AI models?
Imagine a scenario where an AI model provider starts acting up. Maybe they were overloaded. Instead of taking 2 seconds to respond, they are taking 30 seconds. Or they are throwing internal server error messages 50% of the time.
Okay, so the model is struggling. It's gasping for air.
Now, imagine your application keeps sending thousands of requests per second to the struggling model, and your users, being impatient humans, keep hitting retry.
It's a pileup, a traffic jam.
We call it the thundering herd. You are hammering a system that is already down.
You're making the problem worse.
Much worse. And worse than that, your own servers are now stuck waiting for answers that aren't coming. You can actually crash your own infrastructure because all your resources are tied up waiting.
So the circuit breaker opens.
The software detects that the failure rate has spiked above a certain threshold, say 20% of requests are failing. It opens the circuit. This means it immediately cuts the connection. It stops sending requests to that specific model entirely.
So instead of waiting 30 seconds to fail, it fails instantly.
Yes. Fast failure is better than slow failure. It frees up your resources and it gives the model provider a break to recover.
And then what? Does it just stay open forever? Do I have to manually turn it back on?
No, this is the cool part. It goes into a half-open state. After a set period, say 5 minutes, it lets a few test requests through.
It sends a canary into the mine.
Exactly. It just dips a toe in the water.
If the canary survives. If the test requests come back, okay.
If the test requests succeed, it assumes the provider has recovered. It closes the circuit and normal traffic resumes. It is a self-healing mechanism.
That is smart. It prevents a small glitch from becoming a total system meltdown.
It protects the broader system from a localized failure. It's like quarantining a sick patient.
Now, the third strategy is my favorite because it sounds so diplomatic. Graceful degradation.
This is a user experience concept as much as a technical one.
It sounds like aging gracefully.
In a way. Let's say your primary model, the physicist, is completely offline. The circuit breaker has opened. You can't use it. You have a choice.
Choice A. Show the user a big red error message. 404 not found. Service unavailable.
Which is the worst possible user experience. They leave and they don't come back.
Choice B. Graceful degradation.
You fall back to a backup model. Maybe it's a smaller, dumber, cheaper model. Maybe it's a model you host on your own servers, so it's always available. Let's call it the intern.
Okay, so the physicist is out sick. We bring in the intern.
Yes. The intern might not give you the perfect, nuanced, poetic answer that the physicist would. The grammar might not be as good. The reasoning might be simpler. But the intern can still say, I received your message and logged your ticket, or I can't write that full report right now, but here's a basic summary.
So the user gets a slightly less perfect experience, but the application still works. The core function is still there.
Exactly. It degrades gracefully. It is better to give a functional, slightly lower quality answer than to give an error message. It keeps the user engaged.
It builds trust. It shows the system is robust.
And this connects back to our router discussion. Your router logic can be programmed to say, if Genius model fails, automatically route to intern model.
It's all connected. The ecosystem is starting to make sense.
It is. You are building a safety net with multiple layers.
Okay, moving on to section 4. We've selected our model, we've built a router, we've made it resilient. Now we want to make it ours. This is the customization lifecycle.
This is where we move from generic to specific. Out of the box, these foundation models are generalists.
They know about Shakespeare and Python and cats on the internet,
Right. They know Wikipedia, they know Reddit, they know open source code.
but they don't know my business. They don't know my internal acronyms, my specific coding style, or my customer service tone.
Correct. To them, you are just another stranger. We need to teach them. The source mentions two main ways to do this: fine-tuning and PEFT. Let's start with the traditional method, fine-tuning.
I hear this term a lot. We need to fine-tune the model. What does it actually involve?
Fine-tuning is the heavy lift. It essentially means taking the model, all those billions of parameters, and sending it back to school. You are retraining the entire brain on your specific data. You are updating all the weights.
That sounds expensive.
It is extremely expensive. It requires massive GPU clusters, it takes days or weeks, and it requires a lot of clean data. But it has another risk: catastrophic forgetting.
That sounds like a heavy metal band.
It's a nightmare for data scientists. Sometimes when you teach the model your new data, say your internal legal handbooks, it overwrites its general knowledge.
Oh, no.
Suddenly, it knows your legal codes, but it forgets how to speak grammatically correct English, or it forgets how to do basic logic.
You turn the genius into an idiot savant.
Exactly. You've specialized it so much that it's lost its general intelligence.
So the industry has shifted toward PEFT.
Yes, that's right. The source mentions parameter-efficient fine-tuning, PEFT.
Okay, break that down for me.
PEFT is a fascinating breakthrough. It says, don't retrain the whole brain, leave the physicist alone.
So you freeze the main model, you make it read only.
You freeze the original model, you don't touch a single weight. Instead, you introduce a small number of new trainable parameters. Think of them as adapter layers or add-ons. You only train these small layers on your data.
The source uses the term LORI, low-rank adaptation. We discussed an analogy in prep for this that I really loved: the textbook and the sticky note.
Yes, let's use that. Imagine the foundation model is a massive, expensive, 1,000-page encyclopedia of the world. That's GPT-4 or Llama 3.
Okay, the source of all knowledge.
Full fine-tuning is taking a red pen and rewriting every single page of that encyclopedia to add your company's information. It takes forever, you might make mistakes, and you end up with a messy, ruined book that only works for you.
And Laura.
LORI is like taking a transparent yellow sticky note. You write your specific local information on the sticky note. In this company, we define revenue like this. And you slap it onto page 42.
You don't change the book itself.
You don't touch the original book. When the model reads that page, it looks through the sticky note. It sees the original knowledge plus your modification.
That is so much more efficient. It feels cleaner.
It is drastically more efficient. A LoRa adapter might be less than 1% of the size of the original model. You can train it in hours for a few dollars instead of weeks for thousands of dollars.
And you don't risk catastrophic forgetting.
Exactly. The encyclopedia remains intact.
And here is the kicker. Can I have more than one sticky note?
That is the killer feature. You can keep the one base model, the encyclopedia, and have a stack of different sticky notes.
So, one for each department.
You can have a legal sticky note, which is one adapter, a marketing sticky note, which is another adapter, and a code debugging sticky note, which is a third.
And because they're small, I can swap them in and out instantly.
Exactly. Depending on the user's question, the router, our friend from section 2, can say, oh, this is a legal question, load the legal adapter, snap, it's there.
That is modular intelligence. It feels like installing a plugin in a browser.
It is. It transforms customization from a massive infrastructure project into a lightweight software management task. This is supported by platforms like Amazon SageMaker, which manages this training and adaptation process.
It feels like this is the future of customization. Why
Yeah.
would anyone do full fine-tuning if you could just use adapters?
Well, sometimes you do need to fundamentally change how the model behaves, like teaching it a completely new language or a biological sequence it's never seen. For that, you might need the red pen. But for 90% of enterprise use cases, teaching it a specific tone or a specific set of documents, PEFT and LoRa are the way to go.
Tweaking rather than retraining. I like that.
It makes customization accessible. You don't need a supercomputer to train a LoRa adapter. A single GPU can do it.
But of course, with great power comes great responsibility. Or at least great confusion if you don't keep track of things.
That's very true.
This brings us to Section 5. Governance.
The boring but essential part. The vegetables of the meal.
The registry and the rollback. The source asks a terrifying question. What happens when you tweak a model and it gets worse?
It happens all the time.
Really?
All the time. You train a new adapter to make the chatbot friendlier, and suddenly it starts hallucinating facts. Or it becomes too friendly and starts flirting with customers.
Oh boy, that's a support ticket I don't want to see. So how do we manage this chaos? The source talks about a model registry.
Treat models like software artifacts. In software development, we have version control. We use Git. We know exactly which line of code changed, when, and by whom. We need the same discipline for AI models.
So the model registry is like a library catalog for these sticky notes.
Yes. Or a version history. It tracks every version. This is model base v1.0. This is the Customer Service LoRa Adapter v2, trained on Q1 data by engineer Steve. This is v3, trained on Q2 data.
You need to know exactly which iteration is live in production.
Traceability is key. If a customer complains that the bot was rude to them on Tuesday at 2:00 p.m., you need to be able to look at the logs and say, that was adapter v2.1. It had a bug.
You can't just shrug and say, the AI did it.
No, that is not an acceptable answer in a regulated industry like finance or healthcare. You need an audit trail.
And that leads to deployment and rollback strategies, the undo button.
The safety net. If you deploy that new friendly adapter and it starts hallucinating, you need to be able to hit undo immediately.
How fast?
Ideally, it should be automated. We use a technique called canary deployment.
Like the canary in the coal mine. We're back to canaries.
Exactly. You don't roll out the new brain to 100% of your users at once. That's how you cause a major outage.
So you test it on a small group first.
You roll it out to 5% of your users. You watch the metrics like a hawk. Are the error rates going up? Is the sentiment going down? Are users clicking thumbs down?
If the canary dies.
If the metrics look bad, the system automatically rolls back those 5% of users to the old, safe version. No human intervention required.
So it's not a person panicking and hitting a button.
The best systems do it automatically based on predefined alarms. The bad update is rejected before it hurts the majority of your customers.
So it pulls the bad sticky note off the book and goes back to the clean page.
Exactly. The source sketches this life cycle: training, registration, deployment, monitoring, rollback. It is a cycle, not a straight line. You are constantly iterating, testing, deploying, and occasionally retreating.
It sounds like traditional software engineering, just applied to these weird, probabilistic alien brains.
That is the perfect summary. We are trying to wrap reliable, deterministic engineering practices around unpredictable, probabilistic, biological-like entities. It is a clash of cultures, but it is necessary for building real products.
Zoom out. We've covered a huge amount of ground here. We started with the wow, and we ended up in the server room.
Which is where the real work happens.
Let's recap the journey. We started with the selection matrix. We learned that biggest isn't best.
Definitely not.
We have to stop shopping for Ferraris and start hiring the right team. We have to match capabilities, respect constraints like tokens and latency, and face the business reality of cost and licensing.
Right. We stopped chasing the hype and started doing the math.
Then we built the model router. We used Lambda, API Gateway, and app config to create a utility grid.
The traffic cop.
We decoupled our app from the model provider so we can switch brains without rewriting code.
Critical for flexibility and negotiation power.
Then we talked resiliency. We admitted that things break. We talked about multi-region deployment to survive hurricanes.
Or backhoes.
Or backhoes.
Yeah.
Circuit breakers to prevent traffic jams. And graceful degradation so we never show a 404 when we could show a good enough answer.
Reliability over perfection.
Then customization. We moved away from expensive, risky fine-tuning and embraced PEFT and LoRa, the sticky notes of the AI world.
That's the one.
Modular, efficient, swappable intelligence.
Efficiency and specificity.
And finally, governance. The model registry and rollback strategies, keeping track of our versions and having a safety net so we can sleep at night.
Control and safety. It's about professionalizing the process.
It's a comprehensive ecosystem. If you do all these things, you aren't just using AI. You are running an AI platform.
It is. And if I can offer one big takeaway from all of this source material,
Please do.
the model itself is becoming a commodity.
A commodity, like oil or wheat.
In a sense, yes. The genius in the box is getting cheaper, faster, and more common every day. Everyone has access to GPT-4. Everyone has access to Claude. Everyone has access to Llama.
Right, the brain is not the differentiator. If everyone has one.
The competitive advantage for a company isn't having the best model. The competitive advantage is in the orchestration. It is how well you manage this life cycle.
So it's the stuff we've been talking about for the last hour.
Exactly. How fast can you switch providers? How resilient is your system? How efficiently can you customize that model to your specific data using adapters? That is where the value lies.
It's not about the engine. It's about the car you build around it and then how well you drive it.
Exactly. The engineering around the model is now more important than the model itself. That is the moat. That's what's defensible.
That is a powerful shift in perspective. It puts the power back in the hands of the builders, not just the model creators.
It does. It democratizes the power.
Before we go, I have a thought that's been nagging me. We talked about this dynamic selection, this router that picks the best model based on cost or speed.
Yes.
Right now, we humans configure that router. We tell appconfig, use model A because it's cheaper.
Right. It's a manual setting.
But if we take this to its logical conclusion, in the future, will humans even pick models?
That is the provocative question. Where does this end?
Could the router be an AI itself?
I think that is inevitable. In fact, it's already starting.
What would that look like?
Imagine a router AI that analyzes every single prompt coming in real time. It looks at the complexity, it checks the current spot price of tokens on the market, it checks the latency of every provider in that exact moment.
So it's like a high-frequency trader on Wall Street.
Exactly. It negotiates the trade for every single sentence. It would say, oh, this is a simple greeting. Send it to the cheap, fast model that costs 1/100 of a cent. Oh, this is a complex medical diagnosis. Bid for the high reasoning model from the provider who has the lowest latency in the West region right now.
So we end up with a market where models are bidding for our attention in milliseconds.
A fully automated, algorithmic marketplace of intelligence. And the human engineer just sets the budget and the quality threshold and lets the machine handle the logistics.
That is both terrifying and exhilarating. The AI managing the AI.
It is the definition of the future.
Well, on that mind-bending note, we are going to wrap up this deep dive. Thank you for exploring the engineering reality of foundation models with us. It's been a dense one, but hopefully a valuable one.
It was a pleasure. Keep building and build it reliably.
And to you listening, thanks for tuning in. Go check your token limits, build your routers, and we'll see you on the next deep dive. Goodbye.